All right, welcome to Power Plant. In this semester, we're going to cover all things engines, from reciprocating engines, where we're going to start, and we're going to build our foundation and our understanding on reciprocating engines, and then we're going to progress into the more complex turbofan, turboprop, turbojet engines, and then we're going to also talk about propellers and rotors as well. They may seem like more of an airframe type thing, but since they attach directly to the power plant, this is where the FAA wants us to cover it, and that's what you're going to be tested on. All right, so let's first get started by just like learning some basic power plant, some internal combustion engine theory. Okay, so every engine, regardless of what type of engine we're talking about, can be broken down into 4 phases of operation. One is the induction phase, where it starts to suck air in. The next is the compression phase, where it starts to squeeze the air and it starts to pack it in, so that way the fuel can be added to it. Because in the next phase, the ignition phase, that fuel is going to get lit off and it's going to create an explosion, and that explosion is going to be used for work, and then it's going to pass through the engine in the exhaust phase. It's going to go off. You can always remember this from a simple forward progression. Suck, squeeze, bang, and blow. It's going to suck the air in, it's going to squeeze the air, it's going to bang the air with fuel and a spark of some variety, and then it's going to blow it all out and to get rid of it so that way we can do it all over again. Now, this is true of jet engines. It just does it in a nice little straight line. It's true of 4-stroke reciprocating engines. It's true of 2-stroke reciprocating engines. It's even true of rockets with some slight modifications, but the basic thing is still happening. It's still going to take fuel in, it's still going to bang it, and it's going to shoot it at the back, and off you go. This is just engines in general. So it doesn't matter if it's a Weed Eater, or if it's Starship, or if it's a 777, or if it's a Piper Cherokee. All of them follow these same 4 principles in some way, shape, form, or fashion, with little nuances along the way depending on the type of engine that it is. But this is basic internal combustion engine theory. Suck, squeeze, bang, blow. It's that simple. Okay, since this is our first video on engines, we want to talk about just some basic engine terminology that's going to get thrown around a lot, and we want to put some definitions to it so that way we all understand what we're talking about. First one that we're going to talk about is work. All right, so what is work? All right, work is nothing more than the force required to move something over a set distance. That's all that work actually is. It's just force times distance equals work accomplished. All right, horsepower. Horsepower is another one. Think about put yourself in the time period whenever the engine first came around. It's like the Industrial Revolution. Everybody's actually using horses. Horses made it all the way through World War I, and horses are even still being used in World War II. There's like famous episodes of like Band of Brothers where they end up shooting up a bunch of dudes on a horse cart, like I think on the night that they jump into Normandy. If you watch the movie Fury with Brad Pitt, they'll talk about like how they killed so many horses during the first days of Operation Overlord. The reason being is that horses were still widely used. They were cheap, they were readily available, the infrastructure was already set up for horses, and so it became natural to compare the work of a horse with the work of an engine, and so that's how you get 1 horsepower, 1 power of 1 horse. So you think like a 100 horsepower engine, those are really attractive because it's like having 100 horses and you don't have to feed it. Really, I mean, I guess you have to put fuel in it. It doesn't poop. It doesn't take up a lot of space. It's really difficult to steal. Whereas like 100 horses, you kind of like round them up and they move on their own. 100 horsepower engine, you got to pick it up and move it yourself. And they didn't have a car to go through it in the back of the time. So I guess you're either loading it up on your horse or a wagon, or you're running off with it by foot. Either way, it had some advantages. So what is a horsepower? Okay, 1 horsepower is equal to the foot-pounds per minute divided by 33,000. It's a ratio between foot-pounds over 33,000. Remember, work is the force, this time rated in pounds, how much weight it has to go over distance, or multiplied by distance. So you'll say, foot-pounds, that's that work. work done inside of 1 minute divided by 33,000. Now you can also do it by seconds and divide it by 550 pounds. Okay, so piston displacement is nothing more than the volume of a particular cylinder, if you're talking about just piston, right? That's going to be area times height, or displacement equals the size of the piston, the area, the head of the piston, and multiplied by the stroke, the length of the piston has to travel. That gives us the cubic inches of how much volume that that piston is displacement. So you'll hear displacement thrown around a lot in engine talk, and so they're like, well, what is that? That's what they're talking about. The amount of air inside of that cylinder that's actually getting displaced every time that engine turns over. So if you think if you had a 6-cylinder engine or an IO320, if we're going to stick with the IO320 as kind of like our conversation for the rest of the video, it has 4 cylinders. So you say if the displacement is 10 cubic centimeters, well, then you would multiply that times 4. So now it's 40 cubic centimeters of displacement. Now, I have no idea what the IO320's displacement actually is, but that's how you would figure it out. So anytime you hear displacement, this is what they're talking about. All right, let's talk about indicated horsepower versus brake horsepower. Now, people will throw around brake horsepower all the time. They'll say like, this engine has 100 brake horsepower, and people are like, oh, but like they don't really know what brake horsepower actually means. Then it's because they don't know what indicated horsepower actually means. Indicated horsepower is the amount of power that the engine actually develops without any sort of friction being taken into account. So it's always going to be higher than your brake horsepower, because the brake horsepower takes that friction into account. The way that we calculate indicated horsepower equals plank divided by 33,000, where plank stands for P is the indicated mean of effective pressure in PSI. So that's how much pressure that the engine is developing. L is the length of the stroke, so how long that piston is moving up and down. A is the area of the piston head or cross-sectional area of the cylinder in square inches. All right, so now we're kind of this. So here's your displacement right there, and this is the actual pressure, which is usually, the usuals. N is the number of power strokes in a minute, so like RPM. So this is going to be expressed as like 2 strokes per minute or whatever the particular is of that engine. And then K is the number of cylinders. So in our case with the IO320, this is going to be 4. You'll total all that up, divided by 33,000, and that gives you the amount of horsepower that is indicated for that engine. Now let's look at brake horsepower. Okay, brake horsepower is totally different. Whereas indicated horsepower is going to measure a lot about the engine internally, brake horsepower is going to be a lot more focused on torque. All right, so torque is nothing more than the amount of twist that's being placed on an object. We're going to measure that amount of twist by force times distance. All right, now once we've figured out the torque of an engine, we can then start to extrapolate how much brake horsepower actually is there. We know the torque, so we have this number right here, and we can start to figure out the work per revolution by multiplying torque by 2 times pi. And that will give us our work per revolution. Okay, so the final step in figuring out our brake horsepower is to take our newly found work per revolution, multiply it by the RPMs of that engine, say 2,000 or whatever. And then once we have that number, we'll divide it by 33,000, which if you remember is like our magical horsepower number. This will actually spit out a number that is our actual brake horsepower at the wheels. So whenever you put a car on a dyno or use a pony device to actually figure out how many brake horsepower you actually have, you can then look at your indicated horsepower on the other side. And you say like, oh, well, this is what brake horsepower is, but indicated says this. And that will tell you how efficient or inefficient your actual engine and your drivetrain is. You can look and say like, okay, well, we have 100 indicated horsepower, but we're only getting 50 brake horsepower. That means that we're losing 50 horsepower somewhere in the midst of that. And the older an engine gets, the older a drivetrain gets, the more horsepower loss you'll actually have. if you like to watch like old car shows and stuff, they'll always make a joke that like, oh well, this is supposed to have 1,000 horsepower, and then they all laugh because they know that this car is super duper old, and so they only know that it has like 200 horsepower because of all the wrongness that's going on inside of the engine. When you look at an aircraft, it's the same thing. The engine may be rated for, say, climbing at a certain airspeed, and because it's rated at a certain horsepower. But the thing is that like as the engines age, as they wear down, as they break down, they have a lower and lower brake horsepower. They just get wore out, just like people do. Like my grandma can't run a marathon the way that my cousin can. It's just because one of them is in their 90s and the other one's in their 20s. It's really that simple. So that is the difference between indicated horsepower and then brake horsepower. Okay, now let's talk about friction horsepower. All right, and there's nothing really more to talk about than what we already have. It's simply indicated horsepower minus the brake horsepower, and that will give you the number of how much horsepower that you've lost in the production of that brake horsepower. It's just a more succinct way to say like this is what we should be producing or what we actually are producing versus what we are actually receiving at the wheels or on the prop or whatever. And that difference between the two is friction horsepower. Okay, so compression ratio. We talked a little bit about this in general when we were talking about ratios. Now let's dig into and figure out what exactly a compression ratio is. So here's a definition out of the book. The compression ratio of an engine is a comparison of the volume of space in a cylinder when the piston is at the bottom of the stroke of the volume of space when the piston is at the top of the stroke. So let me draw this out. So if you have a jug, and you have a cylinder, or you have a piston that's going in there, you have a space. And so this is going to be bottom dead center right here, all right? There you're at BDC, and say it's 10, okay? Then whenever you have the same piston comes up, let's say at top dead center, so there's TDC, we'll do it over this side, it's 1. So this has a compression ratio of 10 to 1. That simple. And so that allows you to get a feel for what that piston's travel is inside of the various strokes. Okay, so why do we want to know the compression ratio? Why is it relevant? Let's just keep reading in the book here. It says compression ratio is a controlling factor in the maximum horsepower being developed by the engine. So different compression ratios, that controls the total power the engine can actually develop. But it's limited by present day fuel grades and the high engine speeds and manifold pressures required for takeoff. All right. For example, if there are 140 cubic inches of space inside of a cylinder when the piston is at bottom dead center, and there are 20 cubic inches of space when the piston is at the top of the stroke, the compression ratio will be 140 to 20. This ratio is expressed in this fraction form, which would come down to being a 7 to 1. So 140 divided by 20 is 7 to 1. That's a 7 to 1 compression ratio. The limitations placed on compression ratios, manifold pressure, and the manifold pressure's effect on compression pressures has a major effect on engine operations. Manifold pressure is the average absolute pressure of the air or air fuel charge and the intake manifold, and is measured in the units of inches of mercury. So you'll hear people talk about like when they're flying complex airplanes, they're like 29 inches, or rules of thumb like 1 inch of manifold pressure equals 100 foot a minute drop or climb or whatever. So that's what they're talking about. How much air is going into the engine translates into power. All right, manifold pressure is dependent on the engine's speed and the degree of supercharging, which we haven't got the supercharger yet, so just table that. The operation of the supercharger increases the weight of the charge entering the cylinder, and when a true supercharger is used with an aircraft engine, the manifold pressure may be considerably higher than the pressure on the outside of the atmosphere. The advantage of this condition is that a greater amount of charge is forced into the given cylinder volume, and the greater output of the horsepower results. Okay, that's good. Okay, another type of horsepower that we need to be aware of is thrust horsepower. This is simply taking the brake horsepower and then correcting it for propeller efficiency. So if you have 100 brake horsepower being delivered to the prop, and we know it's 100 on the money, but the prop is only 50% efficient, well, we only have 50 thrust horsepower. That's only 50 horsepower actually exiting the aircraft in form of thrust to move the aircraft. So the higher efficiency the propeller is, the more you're going to get from your engine. Now, what the more you're going to be able to take from your engine and convert to actual work, And so the way that actually matters to the pilot is that, like, I can do more with less. And so if I have 100 horsepower, and I know 100 horsepower gets me in the sky, if I have a high efficiency propeller, I don't have to keep on throttling past that 100 horsepower to get to the 100 horsepower of the thrust horsepower, if that makes sense. So essentially, if you have a 100% efficient horsepower, which you won't, then whatever you set your engine horsepower at, that's what the propeller should be producing. However, there's a lot of reasons why that propeller will be less and less efficient. If it's old, if it's tore up, it's not taken care of, you're going to lower the propeller efficiency every single time. However, if you want to improve that, maybe you get a different propeller, a higher pitch propeller, blend out any dings or scratch, make sure it's balanced right. All those good things all matter for the thrust horsepower. Okay, so now that we have kind of a common vernacular, common understanding of the different terms that we're going to use talking about engines going forward, let's continue our talk about horizontally opposed engines and their components. All right, we're going to start by building our understanding on reciprocating engines, recip theory. You'll hear recip used a lot, and that's just short for reciprocating. All a reciprocating engine is doing that suck, squeeze, banging blow using a piston. Now that piston is going to have multiple strokes. All right, the first stroke is going to be the induction stroke, the intake stroke, where it's going to pull down. Now, but the cylinder, if you imagine this cylinder with this piston sitting in there, is airtight. So, a good engine that's still, the compression is still good in it, you can take the spark plugs out and you can spin the propeller and you'll hear the air go into it. And you'll also be able to put your thumb over the hole and then keep spinning the propeller. And as the piston comes back up in the compression stroke, it'll blow air out of it. And that's how you know that you have good compression. And we're going to teach you how to check it so that way you know quantitatively that it's a good compression. But either way, so to understand the induction stroke on a reciprocating engine, you have a piston with piston rings that creates a seal on the side walls of the jug or the cylinder. All right. As the piston comes down, this valve, the intake valve, is going to open up and allow air into the cylinder. All right. Then when it comes back up, it's going to close that valve, and we'll get to how here in a little bit. As the valve closes, the piston is going to come up and squeeze that air in the compression strokes. Remember, suck, now squeeze, all right? Then you're going to have fuel injectors depending on the type. You have a carbureted and then the fuel injected engines, a little bit different. We'll get to that here in a minute. But you're going to have fuel that's added to that air as it gets squeezed. Now, once the piston hits a point called top dead center. So remember that the piston goes up and down. So bottom dead center is whenever the piston is at the bottom, and then it's not going to go any lower. And then top dead center is whenever the piston is at the top. It's not going to go any higher. So at top dead center, the spark plugs will start to spark. All right. Now it actually does it right before, we'll call it the spark advance. It does it right before it hits top dead center. So ideally, as the piston is coming up to a top dead center, the pistons or the spark plugs have already started to spark and create an explosion in there, so that the two meet, kind of this nice little equilibrium where it gets the most out of the subsequent explosion that happens after that. Now, as it explodes, it's going to push the piston back down. As the piston pushes back down, what the piston attaches to is the crankshaft. That crankshaft is going to spin as the piston pushes it back down, because the crankshaft is set up in like a jagged pattern, and that as the crankshaft goes around, it's moving the piston up or down. And we'll get into that here in just a little bit. As the piston comes back down. It takes all of that power, spins the crankshaft, which then goes on to be used as actual work somewhere else. All right. So we've got the suck, the induction phase, the sucking, the squeezing phase, the compression phase of engine operation, and then the bang, which is going to be the fuel and the spark plugs. Bang, boom. That happens, and then as it goes back down, the exhaust valve is going to open at bottom dead center, and then the piston is going to come back up, and it's going to blow all of the exhaust, all the smoke and stuff that you see coming out of your tailpipe starts here, and then goes out the exhaust, then out the exhaust manifold, and then exits the airplane through the whatever their exhaust system is. But that's it. That is reciprocating engine theory. Now there's a lot more to it. There's all kinds of, like, where does the spark come from? So it's going to have like magnetos or coils or whatever. How does the work get transferred from point A to point B? How does the piston attach? These are all details that we're going to cover in later videos. But for right now, all we really need to remember is suck, squeeze, bang, and blow. The induction phase, the compression phase, the ignition phase, and then the exhaust phase, if you want to be prim and proper about it. But they all mean the same thing. It's just easier to remember the 4 smaller words. So that is reciprocating engine theory. Okay, so the foundation of every engine, any engine, is going to be the crankcase. This is what gives the engine its shape, form, and allows everything else to happen. It also provides a space to house all the engine oil, which allows the engine oil to swirl around, clean the engine, and then drop the engine oil temperature by that. And we'll get more of that in the engine oil theory section. However, there's 2 things that we need to take away from the crankcase. Number 1 is the nose of the crankcase. This is where the propeller mounts up to. So if there's a propeller governor, reduction gears, or anything else like that, it goes on the nose, the forward end of the crankcase. The other one is probably even more important for especially for GA guys, is the accessory section of the engine. This is where, like, all your vacuum pumps, your magnetos, anything that is unique to that engine is going to be mounted back here. That's going to use the engine power, or is going to be a critical component to the functions of the engine. If it gets mounted directly to the engine, it's going to happen back here in the accessory. Now, the heart and soul of an engine really is the crankshaft. That's where everything comes together, from the load that it's going to be carrying, so in this case the prop, to the pistons that actually produce the actual power itself. Everything gets tied together to the crankcase, or to the crankshaft rather. Now, the crankshaft, it does not look like a shaft, like in the way that you would think of, that it's just like a long pole or something. Instead, it has all of these little angles and little jogs in it that are called throws. Now, on the top, and these are they can also be multi-pieces or single pieces. These are 2 single-piece crankshafts. The one on top is a 4-throw crankshaft, which is going to come from like a 4-cylinder engine. So you can imagine every throw is where a piston attaches itself to. So that's a 4-throw engine for a 4-cylinder engine, because you're going to have 4 pistons attached to it. The bottom is a 6-throw crankshaft from a 6-cylinder engine. And now on the right there, you can see how they are opposed to one another. So on the top there, every throw is opposed to 180 degrees, whereas the 6th throw is opposed by 120 degrees. Now, you think about it, and we're going to get into this a little bit later when we talk about engine types, but imagine the vibrational difference between the 2. Like, whereas with the top, you have like some pistons that are firing, and some of them that are just recovering, that are in the exhaust phase, or maybe the induction phase of operation. And the bottom, though, you have one bank of pistons that's firing, one that's exhausting, the other one that maybe inducing, and so you get a lot more smooth operation because of the extra bank of cylinders that helps kind of dampen out the vibration. One of the kind of classic examples of this is look at the vibration that happens with single cylinder, like dirt bikes. They call them thumpers, and they call them thumpers for a reason. They make that dum 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 whenever they're running, because there's just
a single cylinder that's firing, and there's not like an opposed cylinder like you would get on like BMW like GS 1200s or something like that. You or even like a cut V like on a Harley Davidson. Instead, you have just that single cylinder. And because you have that single cylinder, you get a lot more vibration in the ride because of the single cylinder that's firing and then going through the whole cycle by itself, and there's not another cylinder to help kind of like offset it at all. But anyway, either way, these are all just examples of crankshafts. All right, and this is kind of like an idea of how a crankshaft actually operates. You can see that the crankshaft motion is spinning there with the flywheel and the power sprockets on the end, and on that far right hand side you have the arrow that shows the crankshaft motion as it spins around. But then it's attached to all the different piston rods and therefore the pistons in the different cylinders. And so you can see that the two outermost cylinders are on one phase of operation, probably the exhaust phase. And then the two center cylinders are on like their compression phase, to where they're going to fire and then go back down. And as they push the crankshaft down, the other throws are pushing on those rods that are pushing the pistons into position for the next round of firing. And so you can see where the crankshaft really is kind of like the heart of the entire engine. Now, the book actually says it's the backbone. I don't agree with that. I think that the case itself is the backbone. It's what kind of keeps everything together. But really, the crankshaft is where everything happens, at least in terms of motion. All right, here's a picture of an actual crankshaft, what they actually look like. So a couple of things to look at here. We're just going to start on the left, and we're going to kind of like work our way down. We have a dotted line, or ghost line if you want to use aircraft drawing terms, that kind of shows where it's going to rotate. So it's spinning around that dotted line. Now you have a flywheel, starter, ring gear, flange. So effectively that's what attaches the rest of the engine to the crankshaft. So like the propeller or whatever is going to mount to it goes on to that flange there and tightens down. So that's something to kind of keep in mind, is that like that propeller is really kind of showing you, unless it has a reduction gear, which the more advanced aircraft are going to have stuff like that. But either if it's just like a regular like an IO 320, that's pretty straightforward. That propeller is showing you kind of what's happening in the engine. It's also how you're going to manipulate the engine whenever you go to do compression tests and magneto timing and things like that. It's just by grabbing it and then turning the crankshaft. And as you turn the crankshaft, you also move the pistons up and down. Now, the next thing is like notice the oil passageways that are called out in all of those throws. Now, that crankshaft is going to be exposed to just oil that's just sitting there, and we'll get to what we call a wet sump system, and so that's splashing that oil as it goes around. And those passageways are going to allow oil to creep into the rest of the engine. They're just going to grab the oil and it's going to sling it up on top. So that way it grabs that heat and then helps dissipate it, and also helps clean the inside of the engine. Now, you could say like, well, it's just like a little bitty passageway. How much oil can really get through there? And that's a good point. It's not a whole lot, but whenever it's turning at 2,000 rounds per minute or 2,000 RPMs, it's a lot of oil that gets slung around in there. Now, the other thing is that you have the crank web and crank pins. Okay, now so those crank pins are where the actual your connecting rods are going to attach to, and the web is the connecting piece for the pins themselves. The other one to look at are going to be your main journals. Now, those crank pin journals are a key piece of keeping the crankshaft together. And so like I've actually had engines shear those crank journals, because they'll start to work their way out, and you'll end up shearing one, you'll end up picking up metal in the filters and stuff like that. But just know that those are little just parts and pieces of the crankshaft itself. Okay, so this is kind of a special mention. So out of a radial engine, you might get a single throw crank pin. Now, or crankshaft. Now, these are kind of unique because and when we get to the engine types, you'll start to understand why these exist. The crankshaft on a radial engine isn't really a shaft. I mean, I guess it is, but it's not. It's totally different than like your 4 or 6 throw crankshaft. Instead, it's just you have this single crank pin that the piston goes on. and it spins around and then turns a shaft of its own that then goes into a set of gears that actually turns the prop. Now, what makes this also like totally unique is that you have a counterweight and dampening weights on the other side to keep the engine from just totally having unencumbered what's the right way to say it, like an unencumbered amount of vibration that's just shaking itself to death. And that's something that's unique to just radial engines. You won't see this kind of setup anywhere else. You also, like, at least for the scope of this class, we're going to cover radial engines a little bit, and you're going to work on one while you're in here. But we're not going to tear them down. So, at least in here, you're never going to end up seeing one of these in real life. At least not that we think at this point. You might see the rest, all these other pieces in an engine, but you're not going to see this in particular piece. But just know that it's out there. So if you ever see one that's a counterweight on a single throw crankshaft off of a radial engine. Okay, next comes a connecting rod. The connecting rod is the link that transmits forces between the piston and the crankshaft. Now, this is a connecting rod. You can see that the piston actually connects to the small end there, and then you have the bigger end that actually connects to the crankshaft itself. Now, there are 4 types of connecting rods. One's the plain, the other one's fork and blade, master articulated, and the split type. Okay, so let's look at these 4 types of connecting rods we get. The first we're going to look at is the master articulated rod assembly, because this is going to be the easiest one to explain. It's basically used only in radial engines. That's going to be the bottom right-hand corner. You're going to have a master rod. It's going to turn around, and the master rod is basically joined to the hub, and then the other articulating rods that go into or pinned to the hub, and they can pivot and spin. We're going to get into that more with radial engines here in a minute, so we're just put that one off to the side. The other one that's easy to just kind of explain away is going to be the fork and blade rod that you see on the top right. That's only going to be used for V-type engines, which you generally don't ever see in. As a matter of fact, I can't think of a single aircraft that has a V-type engine in it. I'm sure there's probably one out there that I'm not thinking about, but generally speaking, we use horizontally opposed engines at all, and we'll get to what that is here in a minute. So you can kind of like file that one away, but essentially the way it works is you have a master rod, and then you have a blade rod that can articulate, they can swivel and pivot away from the master rod. Now, the other one is the split type or the solid type master rod that's in the top left-hand corner. Now, that one gets used in a variety of different engines, but it's not one that we're going to deal with in this course. Now, a lot of this stuff, when you start talking about power plant stuff, the internal workings of these engines, especially jet engines, they may start becoming more and more unique with every subdivision of that type of engine that you come across. So, for instance, reciprocating engines, they all generally have pistons, right? But whenever you start talking about the different arrangement of those pistons, you start to change the crankshafts, you start changing the rods and all this other good stuff. So as we go forward, just know that we're going to cover we're going to focus in on horizontally opposed engines because that's the most common one that's out there in general aviation, and that's what we're going to do. That's what we have to use here in the course. But just know that there's other possibilities that are out there, but the same principles generally apply. That being said, where we're going to kind of come to land is the plain rod. That's just like the picture of the one that I showed you before. That's going to be used in a horizontally opposed engine, like a IO320 or IO360, or any one of the Continental engines that we have. And it's probably the most common one that's out there just in general. Now, the plain rod, looking at it, you have a piston pin in that's going to go to the piston itself. There's a bushing, and then the shank is that long, skinny part that you're looking at right there in that bottom left-hand corner. Then you have bearing shells lined with bearing material, so that way it can move around the crankshaft as the crankshaft goes around. Then you have what's called a crimp or pinch or a saddle. So that saddle mount goes onto, and then you have this bottom part that actually comes up, and there's 2 bolts that will go through there that actually connects the bottom part of that saddle to the top part of the saddle, called the connecting rod bolts, and the bottom part of that saddle is called the cap, and that's what connects the piston, the connecting rod, to the crankshaft itself as it goes around. All right, so the piston is probably the most iconic and probably the most recognizable part of the entire engine. This is really where the magic happens. So it's kind of like orienting yourself to that piston itself. If you look at the top, that's going to be the head of the piston. We're going to talk about that a lot more here in just a second. Then you're going to have a series of rings to include an oil control ring and a piston ring. So the oil control ring is going to that sits on the bottom. It basically doesn't let the oil come up. Up into the cylinder, so whatever you get, and this all kind of will start to factor into troubleshooting. When the oil control ring starts to fail, you'll start to get like fouled spark plugs. You'll start to see heavier exhaust because what's happening, especially blue exhaust, you'll start to see you'll start to get oil burning with the fuel up in the cylinder, and the oil is not nearly as refined as the avgas or the automotive gas that's burning inside of that cylinder, and so it'll get a lot more gunky, and that causes all kinds of problems. Then you'll have the compression rings that sit on top of the oil control ring, and that basically keeps a metal on metal contact inside of that cylinder, so that way it maintains the compression. So whenever we do our compression check, what you're looking for, and it could be come from a variety of things, but one of the primary things is the ring still holding that seal the way that it's supposed to? Because if not, then you might need to overhaul that engine, or at least pull the pistons out and replace the rings on it. And that's a common thing that will go wrong inside of these engines, that the rings will fail, and then you end up having to pull a piston out and reset the rings. Okay, so this kind of shows you the breakdown of it. The other component that we didn't talk about is the piston pin. Now, what that pin does is it actually attaches the head of the piston to the connecting rod itself, and then therefore to the crankshaft, and then therefore to the propeller. So that piston pin is absolutely critical. If the pin fails and that head comes off, you're going to hear it, because it's going to make all kinds of hellacious noise as that connecting rod bounces around inside of that cylinder. Also notice that there are a couple of different types of heads. You have a flat head like the one that we looked at that is literally just flat. You have a recessed head which has like little bitty recesses in it to capture, and we'll talk about that here and just why it's there. And then you have a trunk type head that's delved out. Like you'll see these where the piston itself, like the one on the top there has a recessed head, it'll have just one big kind of concave like hollowing out. I don't know how it's got like this little half moon kind of shape that's taken out of the top of the head. And then you have the dome head, which is the exact opposite of that. Instead of being hollowed out, it's domed up over the top. And those are the different styles of heads that you could come across. Now these heads are used for a variety of different reasons. A lot of the times they're trying to accommodate valve clearances, or maybe the spark plug clearances, or optimize for efficiency or power or whatever. Every engine is a little bit different, but this highlights a couple of things. One is that we make sure that we use the right part number on the right engine, because if not, let's say if you have a dome head on a piston, and then you turn around and you install it there. The first time it cranks up and it smacks a valve as the valve is coming down, you've just basically created a lot of problems for yourself. You more or less destroyed that engine. And so at the same time is that if you have like a flat top but you need a dome head, you may not get nearly the compression you're looking for, or the performance that you're looking for. Maybe it runs, but for whatever reason it just does not produce enough power. Well, it's because it's not compressing enough, because the original design accounted for that dome head that's in there, and now it's not there, so you're not getting nearly the amount of squeeze that you absolutely needed. And so it's really important that we use the right part number for the right engine to make sure that we adhere closely to that TCDS approved original engineering of that engine, unless it's been STC'd appropriately. Alright, so probably one of the most replaced pieces of an aircraft engine is the cylinder head, it seems. They'll get too hot, they deform, they just get wore out over time. You name it. So get used to having to deal with the cylinder heads. You'll also hear these called jugs, as as a kind of like a, I don't know, like a pet name for cylinder heads by old mechanics. Most of the younger guys won't ever call them that, but the old guys will. Now, these things have to be strong enough to withstand the internal pressures developed during engine operation. So you think that it has to hold an explosion every, like 2,000 times inside of a minute, and it has to do that for hours on end. And they do. Usually these engines will go for a long, long period of time, and you might end up having to replace a jug here or there. But so be it. They also be constructed of lightweight metal to keep the engine weight down. So you imagine if these were all cast iron, they would get pretty heavy pretty quick. And these engines are still pretty heavy, even whenever they're all made out of aluminum. But like the older engines were even heavier. They also have to have good heat conducting properties for efficient cooling. That's probably one of the most important things on these engines is those cooling fins. Now, what those cooling fins do is the cylinder gets hot on the inside, and the cooling fins increase the surface area of the cylinder. So as it conducts the heat, as that heat kind of distributes out throughout the rest of the cylinder, it has a greater chance of getting away, being pulled away and being cooled down by the air as it comes through the cowling and then exits through the bottom of the cowling. Now, then lastly, they have to be easy to and inexpensive to manufacture, inspect, and maintain. So if you have one of these that goes down, we need to be able to pull it off and then put a new one on without just completely killing the budget. Because you think about like if you end up having a cylinder that costs nearly as much as the engine, that's going to really mess you up for the day. Okay, so the cylinder basically breaks down into two main parts. One is the head, and the other one is the barrel. We're going to talk about the head right now. The head provides the home of all the little inner working parts of the engine, the valves, spark plugs, all that good stuff. That's where top dead center is going to happen, and you're going to have this massive explosion. Now, it's really, really important that it's accommodates all of that, so it's the right cylinder for the aircraft for one. But number two is that it's also important that it maintains a certain temperature. Ideally, like you have two temperature limits on just about any part that you're going to come across. One is like the max temperature it can ever have, period. You think at some point that metal is going to start to melt, or it's going to get close enough where it's going to start to warp and have all kinds of problems. The other thing is that like you're going to have you can't overexpose it to a certain level of heat on a regular basis. So you think about like there's like a red line, it cannot get this hot, period. Then there's like a yellow band where it can't get this hot, but it can get that hot, but it can't do it very often, like once a week or once every so many cycles or so many hours or whatever it is. And then there's like a normal operating temperature that it was built for, and like kind of like a green band of your old temperature. And it says like, hey, look, it can get this hot all the time, and it's not going to matter. Like if it stays within 300 degrees and doesn't ever get to go above that, we're fine. But it can occasionally go to 350, but it absolutely can't go to 400. And that's all managing what's called CHT, or cylinder head temperature. And that's something that a lot of these guys that are getting these engine monitoring modules on their aircraft now, they're paying a lot of attention to that, because what they're noticing is that for one reason or another, cylinder number one really runs hot. The other ones are at 300 all the time, but this one's always at 350, and that's the one that I always have problems out of. Well, it tells me that they're having some sort of like cooling issue. They're all on cylinder head one for whatever reason, and then that kind of helps guide your troubleshooting. And it's usually something really dumb, something like a baffle, or there's something attached to the airplane that's not supposed to be there, or something, but usually that's what's going to be going to boil down to, and it might be just the way that they're flying. Maybe it's like a super fat dude, and like the cowling isn't it's the whole airplane is kind of tilted over one side, and it's not just catching the air right anymore, or whatever the reason being. But the point is that cylinder head temperature will tell you a lot about engine health if you pay attention to it, and it's also critical for engine longevity.
Okay, now every single cylinder has a set number. All right, so if you think like this is going to be your number one cylinder here, and then 2 and 3 and then 4 and so on. Now you might think like, well, why is that relevant? Well, for one, it gives us a way to differentiate one cylinder from another. If we said like, hey, look, the rings are bad on the number one cylinder, people understand what you're talking about. But if you said like, the rings are bad on a cylinder, like, well, which one? I'm like, well, it's kind of the one that's front to the left, but what happens when you pull it off the engine and it just gets really, really messy. But the most important thing that it has to do is a firing order. So every single one of these cylinders fires at a different time. So then whenever this one's like on the compression phase, this one's on the power phase, or so on and so forth. And so like the number one cylinder fires first, then the second, then the third, then the fourth, and then it comes back around to the number one cylinder again. So all of these things matter on when it comes to firing order. So every single one of these cylinders is numbered appropriately. Now most of the time there's some sort of labeling. So like, you know, this Lycoming here, there's a 4 that very clearly denotes this as the number 4 cylinder. There'll be a 1 and a 2 and a 3 somewhere else. Some engines don't have that. And so you have to look at the manual to figure out which engine is what, especially whenever we're doing maintenance and we're trying to figure out, how to set the number one cylinder to top dead center for various things.
All right, so the next component we want to look at is the valves. The valves help modulate or I guess modulate this in the electrical world. It facilitates the movement of the fuel-air mixture and then exhaust in and out of the cylinder. So the air-fuel mixture enters the cylinders through the intake valve port, and then burn gases are expelled through the exhaust valve port. The head of each valve opens and closes these cylinder ports, and the valves used in the aircraft engines are conventional poppet type. The valves are also typed by their shape and are called either mushroom or tulip because of their resemblance in the shape of the plant. So you can see on here you have the tulip type on the bottom left, but in the center top you have the mushroom type, and then you can kind of see how they are slightly different, styles based on the engine that they get used in and the purpose that they're being used for. Now the valve head has a ground face that forms a seal against a ground valve seat in the cylinder head when the valve is closed. The face of the valve usually is ground to an angle of either 30 or 45 degrees. Now, whenever you go to like overhaul an engine, this is something that you may end up having to do. That if the valve isn't completely seating for one reason, one of the things that could happen is either the cylinders become deformed or there's some trash on the valve seat. You might have to rework that so that way the valve seat sits there and forms an appropriate seal. All right, so the valve stem, which is actually the long part that actually connects the seat to the rest of the engine, it acts as a pilot for the valve head and then rides in a valve guide that's installed in the cylinder head for this purpose that you can see right here. Now that valve stem comes to a little beveled end. That beveled end of the stem is hardened to resist wear. Now the neck is the part that forms the junction between the head and the stem, and the tip of the valve is hardened to withstand the hammering of the valve rocker arm as it opens the valve. And a machine groove at the stem near the tip receives the split ring stem keys, and the stem keys form a lock ring that hold the valve spring retaining washer in place. Now, what you're looking at here is that retaining washer and the springs that basically keep the valve shut. So that spring wants to expand out, and the valve seats up against the cylinder, causing it to close until the rocker arm pushes down on that spring, which opens the valve. And then once the cam rolls off, the rocker arm goes backwards and it closes the valve, which we'll look at here in just a second. All right, so this is the valve operating mechanism. You can see the valve spring and the valve guide, the port, and the seat up in the upper right-hand corner. Now, right above that, you have a roller and a rocker arm. Now, what that rocker arm does is it actually pushes on the stem and it pushes the valve open. So the next question becomes like, well, how does the rocker arm get that motion? That comes from a push rod. The push rod pushes the rocker arm, which then pushes the valve stem, and then the push rod gets pushed by a tappet, and the tappet then gets pushed on by a camshaft. Now the camshaft is simply just a circular shaft with like this little divot that comes off, and as that divot comes off, it pushes up on the push rod, that then pushes up on the rocker arm, that then pushes down on the valve stem. And it's all when we talk about timing an engine, this is what we're talking about. We're trying to make sure that the spark advance is set right so that the spark starts lighting off whenever that the intake valve is shut after it's opened up and put atomized fuel into the cylinder, and the exhaust is all out and clear, and then the piston is coming up. And you can see how timing becomes like this major issue for an engine, because there's so much happening mechanically that if you have one of these things off, the engine won't run, or worst case scenario, it damages itself because the piston's coming up when the valve is coming down, or whatever the situation may be. All right, and this is what a camshaft will look like. You can see the little cam ramps that are on either side of that little divot that comes off of the camshaft that's up top. And so you imagine this thing as it's spinning around, and that valve, or that cam roller, is sitting right there on the camshaft itself. As that the little divot comes up, it pushes up on the roller, that pushes the tappet, that pushes the push rod, that pushes the rocker arm, that pushes down on the valve itself. And that is how valves work. You have one for exhaust or one for intake, and sometimes you'll end up having two valves for two for exhaust, two for intake. That happens. Now, some engines you'll see that it'll be advertised as an overhead cam. What it's basically saying is that it's eliminated the push rods, or at least the significant portion of them, and the cams are sitting on top, pushing down on the rocker arms directly. So you lose a lot of lag that way, and you get a lot more responsive engine and a lot more efficient engine by having that overhead cam on there.
Okay, so if we're looking at it from the top down, here's the cylinder head. Here is your valve retainer springs and the spring that goes onto it. This is the rocker arm. These are the push rods, and in the center here, is going to be the cam that then pushes up on the push rod, that then pushes down on this rocker arm, that then pushes, and I can't even get it to collapse a little bit, pushes on the spring to unseat the valve, so that way the fuel can come in, or the exhaust can go in through these two inlets right here. One of them is going to be the exhaust, and then one of them is going to be the inlet off the side. So that's all happening on just this one cylinder, but the same thing is happening on every single cylinder around. The intake and then exhaust is going to pipe into manifolds, either the exhaust manifold or the intake manifold. The intake manifold is going to gather up the atomized fuel and then push it into the individual cylinders. And then the reverse is happening with the exhaust. Is going to gather up all the exhaust and put it together, and then off it goes into the exhaust, or the tailpipe, basically. Now, there's some aircraft that will have straight pipes that the exhaust just comes right there and it goes out, and there is no manifold at all. It really kind of depends. There is a school of thought with reducing the back pressure on the exhaust manifold will help increase the engine's efficiency, and therefore you increase performance. And that's true, it does. But really every manufacturer is a little bit different, because that engine has been optimized for a certain level of performance, and then the aircraft is certified on that. So you don't want to go and start chopping exhaust pipes to try to make them straight pipes or something like that.
Okay, here's a cutaway of that same cylinder. It's a horizontally posed engine, and you can kind of see how the camshaft operates with those different lobes. Those lobes hit the tappet then pushes up on the push rod activates the valve. It's really pretty straightforward, pretty simple. And you got to think that this type of engine was developed well over 100 years ago, and it's been refined and changed and optimized for sure, but the actual just kind of bare bones how it works is not really that complicated or that simple. Now, where you'll get complicated is in some of the tolerances of these things, and making sure that they're assembled the right way, because since you're dealing with such high a level of RPMs and such close tolerances, if things aren't perfect, you can really have a bad day pretty quickly with them.
Okay, so everything we've talked about so far is a 4-stroke engine, meaning that there's 4 strokes to the motor. There's 4 cycles. There are other types as well. There is a 2-stroke engine, really common with small engines, some boat motors, dirt bikes, that kind of thing. You may see some experimentals aircraft out there that might have a 2-stroke. I'm not aware of any, but it wouldn't be out of this world to run into some random niche airplane that was a 2-stroke engine. But you're probably not going to, they're definitely going to be commonplace at all. Another thing that came around probably about 10, 15 years ago was the diesel engine in aircraft. Now, the reason being is that diesel is more affordable, and also whenever you're operating, like say, like third world countries, avgas is really difficult to come by, but Jet A is pretty common, and diesel even more common. And so you saw some people start to experiment with the diesel engine. It's also a lot more efficient, so it made flying a lot cheaper. There were several aircraft that came out, some really nice aircraft. I believe Diamond even had a twin that was a twin diesel engine aircraft. Now, the way that a lot of these differ, whereas four-stroke has those four strokes, two-stroke, they combine some strokes and they operate a little bit differently. Diesel, the primary difference between diesel is that instead of having a spark plug, it has a glow plug. So instead of sparking the fuel into explosions, it heats it and then compresses it. And that combination of heat and compression with the glow plug causes the fuel to ignite and causes it to crank up. And there's some distinct advantages between regular gas and diesel. But we won't get into that here. We're mainly going to live in the four-stroke lane, but I want you to know that there are other types of engines that are out there as well. Lastly, you have a rotary engine. Now, rotary engines they're kind of starting to make a comeback. They started to try to get them going a long time ago, and they were too complicated and they couldn't make it work. Now, I believe Toyota is actually coming out with a rotary engine for a car, and the idea being is that like it's one continuous cycle and has a lot of intermingling parts and pieces that make that cycle actually happen. Kind of like in similar like to almost like a jet engine, except for it still has valves and strokes and all the other good stuff. It's just it is put in a circle and it moves around a little bit more complicated than we need to get. But just know that these are other types of engines out there, along with some different differentiations of engines by their cylinder configuration. Okay, there's several different types of reciprocating engines that are out there. We've talked about the horizontally opposed, where the cylinders are opposed to each other. We've talked about the V, like your V6, like in your truck or whatever. They're set up as a V. You have all different manners. One of the other types that's most common is the radial engine. Now, the radial engine has some distinct advantages over the horizontal engine, but it also is a little bit more complex because you have instead of having like a camshaft, you have a whole different type of setup in this thing, and every one of them has its own individual part. I'll tell you just from experience, they're difficult to time. You take special tools, and you have to get every single one of them right. They also leak a lot. There's all kinds of reasons why to not like the radial engine, but there's also a lot of reasons to like the radial engine. They're probably the most romantic engine that you're going to come across anywhere in aviation. And you're going to work on this R680, which is stamped in 1942, if I recall. So it was flying during World War II. You'll work on that here.